So what we're gonna do, our power lines, at least ours, Tri-County's, our distribution lines, operate at 7,200 volts. So 7,200 volts is what we're gonna put on this power line. Does anybody know what the voltage is coming in your house? Like when you go plug something in, do you know what the voltage is?
120.
120, yep, that's right. So we've got 120, you guys see these cables right here? We've got an electrical panel back here, so we're hooked into it. So we're feeding 120 volts from it into the secondary side of this transformer, okay? Maybe you guys can't see the secondary side. So with the transformer, there's a primary side and a secondary side. This is the primary, the low side is the secondary. So transformers are rated at a voltage, okay? So if this transformer was hanging out in front of your house, feeding your house, we've got 7,200 volts on the line going into the top side of the transformer, and the transformer is rated at 7,200 primary and 120 volts on the secondary. So the transformer is going to transform the voltage. It's going to step it down. Why? Anybody know why we want to do that? What would happen if we put 7,200 volts into your outlets in your house?
You blow stuff up.
It blows stuff up, yes. So we got to step it down to make it more of a usable voltage. So that's what we're going to do. We're going to step it down, okay? But in our case, we're going to step it up because the transformer don't know if the voltage is coming in the primary side, and it's going to step it down. If we put 120 volts on the secondary side, what's it going to do? It's going to step it up because it's going to come through reverse, right? So that's what we're doing. We got 120 volts coming in the secondary, coming out the primary to this cutout. When we close this in, that's going to energize our conductor to 7,200 volts. All right. So this cutout, basically, that is just a high voltage switch. It's just like a light switch, but it's for high voltage. So when we close that, this is our conductor. Anybody know what a conductor is? Guy that drives a train? No? Okay. Well, all right. A conductor conducts electricity, and that's why it's called a conductor. There's good conductors and bad conductors. Really good conductor. This is copper. We use copper. We use aluminum. Gold's a really good conductor. Silver's a good conductor. But the reason we don't use those is because it would be very expensive to build a power line out of silver lines or gold lines. So anyway, so we're using copper here. We use a lot of aluminum. Aluminum is a lot cheaper than copper, but it's not near as tough. Like you'll see, we do a lot of arcs and stuff with this copper, and it's just, it'll hold up better. So we've got an insulator right here. What's the insulator doing?
Making sure there's not power in the pole.
Exactly. Yep. It insulates and keeps the electricity off of our pole. So you have insulator, your conductor. We're coming over here. We've got an OCR, oil circuit recloser, or we refer to them as breakers. You guys familiar with breakers like at your house or your farm? The panel, black breakers, you click them on, off. That's basically what this is. This yellow handle is down right now, so this breaker is open. But this breaker is also like the breakers in your homes, but it's a lot smarter. We'll show you how that operates. So if we would close this handle, power is going to come through this breaker, come out here, to our conductor, over here, to our bird. How does a bird sit on the power line and not get electrocuted?
Heading out the ground.
Right. So he's at the same potential as the line, right? So if we energize this line to 7,200 volts, the bird's sitting here, he's energized to 7,200 volts. He's in good shape because there's no difference in potential there, right? Okay, so we're going to come through. Here's another cutout. This cutout's got a solid door in it. We'll show you the difference in the solid door and fused door in a little bit. So if we close that, we're going to come over here to another cutout. And then we've got another transformer back here. Okay? So how many volts we got coming to the top side of this cutout?
2,200.
7,200. We're coming through this cutout to a transformer that's feeding a house. What's the voltage going to be down here at the house?
120.
120. Good. You guys are paying attention. That's great. All right, guys. Let's let's go through our safety equipment real quick before we start. So Jess has got a pair of rubber sleeves. I'll pass them. Rubber sleeve. So these rubber gloves and rubber sleeves that we use, these are class 2 rubber gloves. They're rated at 20,000 volts, and so we actually work on energized lines wearing this stuff. And the reason we do that is because if we called your school and said, hey, we gotta work on this line, you guys are gonna be without power today, probably wouldn't be very happy with us, right? So we gotta do a lot of stuff energized. So there's a rubber glove. Like I said, the gloves are rated 20,000 volts and they've got a leather protector on them, because if we would get a hole in this leather glove or in this rubber glove, it wouldn't insulate us from the electricity. So the leather protector is just like a leather work glove that protects the rubber. We all wear FR clothing. FR stands for fire retardant. Fire retardant clothing, it won't burn. So as you see, when we start with the demo, we make a lot of arcs. There's a lot of fire, and we want to have like Under Armour nylon clothes on and get in one of these arcs. So FR clothing, we wear dielectric hard hats. Dielectric meaning they're not conductive. Safety glasses, and that helps protect us as we're doing line work. So this stick, Matt's got one and Jess has got one. These are called shotguns, or we call them shotguns. We can do all kinds of stuff with them, working on the line, putting clamps on and off, closing, opening switches. We use these daily. They're rated at 100,000 volts per foot. So that's an 8-foot stick. So they're very good tool. All right, Matt, let's close that right out there and close the brake. All right. So how do we know if that power line is energized or not? No. Can we look out there on that Ameren line and tell if it's energized or not? Can't see electricity, can't smell it, you can't hear it, right? Only time you can hear it is if there's a problem. So go ahead and fire it up. So how do we know we got power? When you see on that top line, you see a power going through. But we got a light on at the house. What if the light bulb's bad? Right? So you can't see it, you can't smell it, you can't hear it. We've got a tool here. Jess has got it named this shotgun. You guys are probably young enough, I don't know if you remember, but we call it a potato masher because it looks like an old hand potato masher. But it's basically a voltage proximity indicator. So we can keep the line up and we can be driving down the road. So if you call us and say my power's out, we get out there, we're trying to figure out what's going on. We can hold this out the window and let us know what line's hot, what's not, and we use it for that. So it's pretty handy tool. Okay, so let's go to the bird. One thing I didn't mention, our bottom conductor, okay? See that bottom conductor? That is basically, we call it a neutral. And a neutral is a ground. It's basically a return to our substations. So it's a current carrying conductor, but it's grounded, so we don't have any insulators on it. Everything's grounded. So, okay, so the bird. Turn it on, Jess. We got 7,200 volts going through the bird. You remember me talking about the difference of potential with static electricity, with your socks and touching something? So the bird's sitting here, he's energized 7,200 volts. Everything's good. He's living his best bird life until he reaches over to the pole, which is at a different potential, and tries to get a worm on top of the pole. So, what do you think? The bird had a bad day? Very bad day, right? Yeah. So like I said, that's a difference of potential. That pole is sitting there operating at 0 volts. Everything's tied to the ground. The bird's at 7,200 reaches over the insulator. So we get this a lot. We have birds, squirrels, you name it, get on top of transformers, on top of cutouts, and they're standing there and they're fine when they're energized and they go to jump on the pole or like this transformer. We have the primary bushing. Can you guys see this red tape on the top bushing? So that's our primary bushing. And sometimes, like in the wintertime, these transformers, they get warm, you know? And the case, the actual transformer is all grounded. So it's all sitting there operating at 0 volts. You got 7,200 volts on the primary, and we get squirrels get up there, and they're standing on the case, and they reach up there and grab that primary bushing, and boom, difference of potential. See it. So, all right, so I talked about conductors and insulators. What do you think? Matt's got a tree limb. Is wood a good conductor or a good insulator? All right, we'll find out. Let's see. We're going to energize this tree limb. So we're going to put, see the jumper on the bottom going to our neutral? That's 0. 7,200 coming to the top of it. Just watch it and see what happens. Can you see electricity? It's energized. Can't see it. Smell it, hear it. What do you think? Insulator or conductor? Conductor's right. Wood is actually a very good insulator when it's dry. Years and years ago, before we had fiberglass sticks, long before me, linemen used wood shotguns, wood-handled switch sticks, and they're very good insulators, as long as they're dry. But what do trees have in them that makes them grow? Water. And water is a good conductor. Water itself is actually not a conductor. The minerals in the water are a conductor. So anytime you guys are ever out and we got obviously trees around power lines, stuff happens, the wind blows trees in the power lines. Anytime you guys ever see that, if you ever see a tree in a power line, just stay away from it because you can't see it. You don't know if it's energized, right? So you're better off to stay away from it, okay? All right. How many of you guys got pools? You got a pool? You got a pool too? Everybody's got pools except us. All right, you clean your pool out? You use something like this? Pool skimmer? You guys, what's the handle made out of? Aluminum. What I say is a good conductor? We use it on our power lines. Aluminum. Aluminum wire, aluminum conductor. So Matt's getting ready to clean his pool, gonna have a good day off. Let's see what happens if he's not paying attention and he gets his aluminum pool skimmer in the power line. Matt's probably not gonna go swimming today, okay? So, guys, this happens quite often. Like, you know, somebody puts in a new house and we'll build an electric service into it, and then 3 years later they buy a pool, put a pool in, and if it's an overhead service or something, invariably they'll put the pool right underneath the triplex or the service feeding the house, or right on top of the underground service feeding the house. It's water and electricity don't mix. So if you guys see this, or you know, say your mom and dad are gonna get a trampoline and they're gonna set it up in the yard, and I mean, we've seen it. Trampolines right underneath triplex services feeding houses. Very dangerous. Pools, trampolines, stuff like that, keep them away from the power lines. And if you see something or you got something like that, just call the power company, call, if you're on Tri-County, call us, we'll come out and look at it and make sure the situation is safe, because this stuff's real and it happens. I mean, it's crazy to think about it, but it does, it happens, okay? All right, so I talked about our breaker. See the handle, see the yellow caution tape hanging down on that handle? That breaker's open. So the breaker's open. We got all our cutouts in, so fire that jet. So that breaker's open, right? So where's our power stopping at? feeding through the transformer over here. Power's gonna stop because this breaker's open, so it's like a switch. Power there, no power on the back side, okay? So let's just, for instance, assume that me and Matt and Jess, and we do this almost every day, okay? We're gonna work on the line down here at this last house, all right? So we come down and we open this breaker to make sure that, you know, we're not gonna have any power down here when we're working. So we open the breaker, we're down here working. Matt has got a balloon in the end of his shotgun. Anybody know what those are called? What kind of balloons those are? Those are called Mylar balloons. You guys know what they're made of? Aluminum. Yeah, and you know, I guarantee we go over here at Kroger, sit in the parking lot for 10 minutes, and you'll see somebody coming out with them with some flowers with helium in these balloons or whatever. So people let them go. So they let them go with helium in them, they go up, and then when the helium wears off or whatever helium does, these balloons float down. So like I said, let's assume we're working down here, we've got the breaker open, we think we're good to go. And this balloon would just happen to fall on top of our OCR up here. Watch the house. We conducting electricity through that. Getting lights on at the house. So basically that breaker that we think we've got open, that balloon's bypassing it, right? So it's feeding electricity down here to the house. So if you guys have, have these balloons, whatever, don't let them go. And if you do, write your name and phone number on it before you let it go. Because they land in, you guys know what our substations look like? Do you? Okay. Like the big, where all the power lines go in, and there's a lot of equipment and stuff in there. We've got a lot of equipment just like this breaker in those substations. And we have these balloons laying in there and they can cause all kinds of problems. And power outages for our members. So don't let them go. All right, you gonna do the shovel? Okay, so if you guys, obviously, we don't only have power lines above ground, we've got power lines in there. All right? So anytime, if you're gonna do any digging or your mom or dad's gonna do any digging, what do you need to do before you start digging? We need to call Julie, okay? Call 811. The state has a program, call 811, they'll come out and give you a Julie locate for any utility that's within that description of where you're gonna be digging. So they'll come out and locate phone, water, power, okay? So, because power lines in the ground are as dangerous, if not more dangerous to you or to us working on them, because you're standing on the ground, right? You're automatically at 0 volts, okay? So Matt here, he didn't get a Julie. He's gonna put a new fence in, he's gonna dig some holes. That's a metal tile space, made out of steel, right? So if you have that tile spade, you got your foot on it and you jammed it right into 7200 in one of our cables, bad day, really bad, okay? So like I said, if your parents, if they're gonna do anything, make sure that they have a Julie. We get Julies daily for the work we do, and there's more and more stuff going in the ground every day, guys. All right, so Matt is gonna rig up our dump truck. So we've talked about insulators and conductors. What about tires? Rubber tires on your trucks, your buses, your cars, tractors. Are they an insulator? They're an insulator? Yeah. Right, that's correct. So rubber, if it was just a rubber tire, what are our rubber gloves made out of? What's this rubber sleeve made out of?
Same thing with the tire.
All right, it's rubber. It's a good insulator, great insulator. But with tires, I'm gonna say most tires, what do they put in rubber tires to make them rigid?
Steel wire.
Steel wire, yeah. They're called steel belted tires. If you guys look, which this thing's getting pretty old, you can kind of see the rust where the steel is. See those steel belts all the way through here? You guys see all that? So steel's a good conductor, right? So we're gonna energize this dump truck, 7,200 volts. Can you tell? You can't tell the dump truck's energized, right? So let's just say, for instance, we have this happen, guys. Let's just say this dump truck driver raised his bed, gonna dump some gravel, whatever, and got it into a power line. He's sitting in the truck. He don't know that he's got it in the line, and it's energized 7,200 volts. Well, this guy, show your guy, Matt. He sees it. He sees him raise it into the power line. And he's gonna run over and tell him, hey, you need to lower your bed. You're in the power line. See what happens. It's not going to end well, guys. Okay. So with the tires, so what would happen? Let's say you're in a vehicle and you wreck, and you hit a power pole. Pole falls, lines come down the vehicle. If the vehicle's energized, the rubber tire is going to insulate it for a little bit. As long as the line stays hot, the rubber is going to begin to melt because it's going to start trying to go to ground immediately through the steel belt in the tire. So the tires are going to burn off, catch on fire. So if this would ever happen, guys, it don't matter if you're in a vehicle, if you're in a tractor, whatever. The best thing to do is stay in the vehicle, okay? Stay in the vehicle until the vehicle becomes unsafe. So what would make the vehicle become unsafe? The tires catch on fire. After the tires catch on fire, what else is going to catch on fire? The vehicle. When that happens, then it's unsafe to be in there. So if you guys are ever in that situation, you have to get out of the vehicle, the best way to do it is open the door, turn sideways, put both feet together, not on the ground, and then hop as far away from the vehicle as you can with both feet together, touching the ground. Now, why wouldn't we want to land like this? Yeah, you could, because there's a difference of potential. Just like the bird, just like the guy that runs up to the truck, the bird was at 7,200 volts, the ground was at 0. When the bird reaches over and touches the pole, there's a difference of potential. Same with this. So the way electricity works when it goes to ground, guys, you ever throw a rock in a pond? There's a big splash in the middle, and then there's ripples, and the farther out you get, the farther the ripples get away from each other. Electricity does the same thing. It dissipates through the ground like that. So right where it's going to ground, it could be, let's just say 10 volts, right there at your vehicle where you're jumping out. Well, you go 3 foot away, and it could be 5 volts. So what's the difference between this leg and this leg? 5 volts, difference of potential, right? So again, if you ever find yourself in that situation, stay in the vehicle and call 911, go call us, power company, wherever you're at. But, so, okay. Any questions so far on any of this? Come on, I like questions. All right, we'll keep going. So, electrical burns. Electricity burns you from the inside out, guys. And so we're operating, like I said, 7,200 volts. The higher the voltage, the lower the amperage. So with higher voltage, you can think of it as like a water hose, okay? So pressure on a water hose. Take a water hose, put your finger over the end of it. When you let it off, it's like, right? A lot of pressure. Same way with high voltage. So high voltage, just like the man that went up to the truck, it's gonna blow you away from it, okay? And we're gonna see that. But like I said, electricity burns you from inside out. So we've got a hot dog here, and the only reason we use a hot dog is because it's the closest thing that we can find that is basically made up like we are. The human body's got a lot of fat and a lot of water, just like a hot dog. So let's watch and see what 7,200 volts does to a hot dog. Burn it up pretty quick, right? So like I said, and a lot of times they'll blow that hot dog off. But electricity burns you from the inside out. Anytime, you know, these two guys and I, we know several people that, I worked with one guy that got electrocuted on a job, and it's not a good thing, guys. So that's why we're doing this, and that's why we want you guys to understand. We're not trying to scare you or anything, but it is dangerous, and if you would get electrocuted, they basically, I don't know, show you, look, it burns you from the inside out, and so for them, for the doctors and stuff to be able to treat your electrical burns, they basically have to start from the inside and work their way out, right? So it's not a good thing. Don't let anybody ever have to go through it. So Jess has switched our transformer from high voltage to low voltage. So now, guys, we're going to be putting 120 volts on that top phase. Okay, 120 is the same thing you plug your phone charger into, you plug anything into. All right. So we're going to put a hot dog on the line at 120 volts. So as voltage goes down, amperage goes up. Okay, you guys ever grab an electric fence, your hand, and grabs you and you can't let go of it? Well, alternating current does the same thing at lower voltages, and that's because the amperage go up. So we're going to energize this at 120 volts. So this could be like you grabbing onto an extension cord that's plugged in, that the insulation's bad or something, and you go to grab it, yank it or something. This could happen. So hit it. Is anything happening? Hot dog's just sitting, right? But it's slowly cooking itself from the inside out. 120 volts. Like I said, with high voltage, it'll blow you away. Low voltage, if everything's just right, like you're grounded just perfectly, you know, you can grab a hold of it and you can't let go. You want to let go, but you can't. So that's why, like I said, it's very important. Any kind of cords and as much electrical stuff that we plug in, each one of us daily, to make sure that all that stuff is safe and that way you don't take a chance on any of this stuff. All right. Any questions on any of that so far? No? Okay. All right, we're going to move on. We're going to show you some of our safety devices that we use on our system. So I talked about the breaker, right? Just like your 20 amp breakers at home, feeding your light circuits and stuff. This is what feeds, I guarantee you, more than likely every one of you in here has had one of these that's feeding your home or your farm or guarantee your school. We use these on a lot of our main 3-phase circuits out of substations, long single-phase taps, stuff like that. You're ever at home, the power goes off, comes back on, it goes back off, comes back on, and it goes back off, and it's off. You guys experience that? Okay, this breaker, that's what's doing that. So Matt, we'll show him that, ground. Matt's put a fault from phase to neutral, right past this breaker. See that? So we're 7,200 to ground. So that breaker, what it does is it's sitting out there looking downstream. Like, you know, got power coming to the source side, it's looking downstream of it to see if there's any faults. That's what it does. So anytime a car hits a pole, I'm not gonna say anytime, it's designed to where if a car hits a pole, a limb falls in the line, a squirrel gets into a transformer, whatever, it's gonna open really fast. Boom. It's gonna open and then it's gonna try to reclose. And it'll do that 3 times. And the reason that we have these is if every time a squirrel got on a transformer and, you know, whatever, and the power locked out, and we had, let's say on a main 3-phase circuit, we got 400 or 500 customers on it, there's gonna be a lot of people unhappy, right? So we've got, the breakers are designed for the fault to clear, hopefully, because a lot of faults will clear themselves. For the fault to clear, close back in, everything goes back to normal, nobody's day's messed up without power, right? So I want you guys to watch see the yellow tape, the caution tape on the breaker handle? Count how many seconds it takes for that caution tape to drop. It hit several times. We got something going on with this breaker. If you can't tell, it's taken a lot of abuse over the years, so it's acting up. But generally, about 3 seconds, and then that breaker handle will fall out. So we also use these breakers. We call it a one-shot. Like anytime we're going to go work on the line energized and glove, we'll put the breaker on one shot to where if there's a fault, let's say we're working on the line and something happens that shouldn't happen, and there's a fault, that breaker will open and it will not reclose back in on us, okay? The next thing we have, we've got a 200 amp cutout. The switch right here that Matt's getting ready to load this fuse door in, we took that solid copper door out and we're putting the fuse barrel in there. So let's say off Highway 15, you guys are familiar with that. We've got 3-phase, you'll have a single phase tap, you know, maybe going feeding 6-8 houses. We'll have one of these there, and basically this fuse is just sitting there, and it's basically one shot. So we put a ground on the downstream side of that fuse, and so we'll give you we'll show. I want you guys to watch that red fuse door and count how many seconds it takes to fall out. Let's get a volunteer, Jess. Who wants to volunteer?
Somebody. All you gotta do is push a button.
Hey, yeah, I'll give you this button first.
Yep. Button on top. Everybody ready?
Watch that red door. Alright, so how many seconds did you guys get? It happens pretty fast, right? So, guys, that is a fuse, and once that fuse blows, you're out of power until we come out there and find the problem, refuse it, throw it back in. And that's about how loud they are. And a lot of times when people call in with no power, they'll call in and they'll say, hey, somebody shot a shotgun right outside my door, and I think my transformer blew up. But more times than not, that's a fuse that's blowing. It's not the transformer.
Story is back in May 15th of 2019, so a little over 2.5 years ago. I was working for an ag retail company, kind of similar to like FS or something, and I was running the semi, loading or going to unload into the sprayer, and the sprayer operator unfolded his booms in the power line. So essentially what happened is basically what they did with a dump truck. Dump truck went in the power line. I touched the sprayer with the dump truck and took all the 7,200 volts in through my left arm here, out through both my feet. When that happened, the operator continued to unfold just by coincidence. And then he realized something was wrong. He got out of the sprayer and had to actually give me CPR to bring me back. Went to the local hospital where I spent an hour or so before I got transferred by medevac to a burn unit in Springfield, Illinois, where I spent 45 days in the burn unit. Because like they did with the hot dog, it burned from the inside out. So it took me at least 10 days to stop burning. When I stopped burning, they were finally able to, or they tried to do some amputations before I was done burning, which didn't work. But in all, I ended up with 9 different surgeries with 4 amputations. They took multiple spots on my hand trying to get ahead of it, which didn't work. So they ended up having to go to where I have it now. When they did that, when the power went into my arm, fried, basically turned my brachialis next to the tricep into mush, and then they had to take half the bicep out of my arm. And when they did that, they put in a cadaver's Achilles tendon, because that's the only tendon long enough in the body to reach from where my bicep is now to where it needs attached on my below the elbow. Which, nice big scar from that. And then several skin grafts, which that's why we kind of got the discoloration here. Then they also had the skin graft on my foot, because I lost all my toes on my other foot whenever the power went through my boot to the steel toes. that burning scene come in through the door. From there, so when I first got there, after I was done burning, the trauma unit just wanted to take my arm up here, which the way of living wouldn't have been quite as easy. And it's a little difficult now, but it could have been worse. But what else do we got? So in all, the injuries I sustained was amputation of arm, amputation of leg were the two main ones. My toes, when the power went in, for some reason it didn't come out part of my head, it blew out the temple muscle. We're thinking it found like the little button on top of my hat when that happened. And then it also perked across my armpit where I had a set of keys in my pocket. I got a nice burn there, and I've got a burn on my leg where the hose was whenever I was hooking the hose on the floater, because I was using my leg as a brace. So some of the things that caused this was we're running hard in the middle of May, so we're right in the middle of our heavy spraying season, as you know, the farmers are in the field trying to get everything planted. And the operator had been broke down for a couple hours earlier that morning, and then been our fourth field we've been on for the day. And we just got in a hurry, is essentially what happened. And when that happened, both of us got in a hurry, and I jumped out of the truck. As soon as he pulled in the field, he spun around and started unfolding as he was pulling up to the truck, and I was grabbing the hose off the truck, and I knew the power lines were there, but I thought he was going to be unfolded before he got there. Got into the line as I was getting the hose hooked on, and didn't realize it because the lines were behind me, so I couldn't see it. But it was just one of those things that if myself or the operator were just taking an extra second to slow down and realize what was going on, or realized how close he was to the power lines, this wouldn't have happened. But it's just one of those things that happened. I'm here to tell you about it, which is something quite miraculous that I'm actually here to tell you about it. But it's one of those things that can't stress enough with power lines is take your time and you're around them. Like they said, for underground lines, you call Julie. Just the word needs to get out there that so that way no one else has to go through this. I mean, I still back home, I still farm, I do everything that I used to do. It just takes a lot longer to get those things